So now we have to visualize the vector in 3D space. So consider a box. Here you've got a box. Need to change the color. Not good on B, on blue. Come on. Yes. Okay. So we've got a box here, and we've got the axis x, y, and z axis. I've got my axis given here. Oh God, not good. As I said, not happy with the new technology. Will this work? Which color will work? Green? Orange. Yes, much better. Okay, so we've got our three axes given, x, y, and z. They are my three axes. Previously, I had two axes. Now I've got three axes. So you consider a box. You've got your three axes, and there's a vector A in it. Okay, as your vector A is in space. So if it's in space, it means it's three-dimensional. Okay. Now, vector A can be defined in terms of x, y. Like remember in 2D, you got a vector, you can split it into two components. I've got a vector, I can split into three components. Okay. Now, just remember for concept purpose, this was my vector, and I was taking a perpendicular distance here, perpendicular angle to get my this component out. I was making 90° with the axis. To get my y component, I was making a 90° here to get my this axis out, component out. So what I was doing, I was making 90° with my axis to get the component out. Okay, is that clear? I will do exactly the same for 3D also. So let's look at that. Now, before we go in, I've got the details here. Yes. Okay. Now, I've got my A vector here. I want to see its component on the Z axis. Okay. So I will make 90° with Z. Okay. So that is basically, I can make 90° here. So this is my Z component out. Okay. I've got my Z component of A here. I made 90° with that axis. Okay. I can do exactly the same for the other two axes, but I'm not going to do that at the moment because there are two different ways of doing this. Okay. So I've got easily my Z component out by making 90° with that axis. I am now going to make 90° with the plane here. This is my XY plane. So I'm going to make a 90° with this plane, which is here. That's my 90°. Okay, so I've got my 90°. So this vector here, this vector is now A dash. Okay. So if you look at XY plane, it's 2D. Okay, so I can, now what you were doing, remember in 2D, you had a vector, you were making 90° with the axis. I do exactly the same here. I've got my 90° here with the axis, and I've got this component. Similarly, I've got 90° here, and I can get this component out. That's basically this component. So what I did, I had a vector in space. To get Z, it was easy. I made 90 with Z axis. So that was easy. I had a projection of vector A on my XY plane. It is the shadow of vector A on the XY plane. So I had my a dash out. Once I've got that in my xy plane, it is 2D. I can divide into two components, x and y. Is that clear? Okay. So that's how I can divide my 3D vector into three components. Clear? Now let's see what it says. The projection of A in the xy plane is A dash. That's here. The magnitude of this projection A dash is found by using the same approach as your 2D. Okay. The magnitude of the position vector A can now be obtained as this. The magnitude, remember when it was 2D, you had two components. Now you've got three components. You can easily get the magnitude out of your vector A. Clear? It's just like 2D. You had two components. Now you've got three components. The direction or the orientation of A, that's now, let's look at the angle. What we were doing in 2D, remember we had a vector and we were looking its angle with respect to X, or we can look at its angle with respect to Y. Okay. Now it's 3D. So we will do exactly the same. We need to see the angle of the vector with respect to X, Y, and Z, because now there are three axes. So what are those X, Y, Z? So let me make it right here. It will be easy then. I've got a vector here, and I was getting this angle out along X. And I was using sine cos for knowing that this is 90. So knowing that this is 90, I was getting this angle out. I'm doing exactly the same for 3D. In 3D, look, I'm looking for this alpha. Alpha is the angle the vector makes with the x-axis. So it is a bit difficult, but no, let me do Z. Z is easy to see that. I want to find out this angle, gamma angle here. Okay, and this gamma angle is basically between your A and Z axis. Okay, so just like in my 2D where I had this 90, I've got my 90 here with that axis, and so therefore I've got my gamma here. Okay, I can use sine cos now. Exactly the same I can do for my y-axis, which is the beta angle. Angle beta is along y, and your angle alpha is along your x-axis. Is that clear? Now, so the direction orientation of vector A is defined by the angles alpha, beta, and gamma. These angles are measured between the vector and the positive x, y, z axis. Their range of values definitely is from 0 to 180 degrees. Now, using trigonometry, direction cosines are found using the formula. I'm not going to go into details, you know this. Okay. This is simple maths, geometry. Okay. These angles are not independent. It means that they are not linked, but they are, no. If they are not independent, it means that they are not affected by, they are affected by other angles. They are dependent. Okay. So they are affected by others. So alpha is affected by gamma and beta. And the reason why is this: they must satisfy this condition. Cos square alpha plus cos square beta plus cos square gamma equals 1. Okay. And how we get this, I've done it for you so you can have a look at it. Okay. So this is the condition that you have to remember in 3D. This result can be derived from the definition of a coordinate, direction, angles, and the unit vector. I've done all the maths for you here, so you can have a look later. This is just, remember the magnitude type thing? If the magnitude, you can do that later. So a unit vector is basically like I did this. I wrote a vector is equal to a and the unit vector of a. Remember? So I can write unit vector a is equal to a vector divided by its magnitude. Very same thing is here. Okay, so the unit vector is basically equal to your vector divided by magnitude. So vector I write in the component form, I divide by magnitude, that is my unit vector. Or I can write it because this is same as this here. So I can write this in place of x square and I can get my cos out. I can write my unit vector in this form also. So I've got two ways of writing my unit vector form. One way is in this form, and the other way is in this form. Is that clear? Okay. Now, so that's my vector. This is my unit vector, and this is basically the A in the component form.